Hi, in this video, we want to take a look at interpolation and geostatistics using R for spatial data analysis. All right, so the code and examples that we're going to run through are from Applied Spatial Data Analysis with R, second edition. Here are the authors of the textbook, and here is the website if you want to check this out. The textbook is available to download for free as a PDF through UCF's library if you're a student. All right, so here we want to talk specifically about model diagnostics. All right, so some ways that we have looked at checking model quality after we built the model is to, first and foremost, look at what values did I get from my model, all right, and look at our residual plots, like the ones from regression, without even considering spatial statistics. Then we could also, spatially plot the fitted values and the residual plots, see if those make sense from our knowledge of what's going on. And we can also do visual and numerical inspection of the variogram models, and we can do visual and numeric inspection of our kriging models. All right, so these are all very natural ways to tackle this problem. So my goal for this is what I'm doing. I want to build a model, and my goal is either inference or prediction. So inference, I want to understand what's going on overall. For prediction, let's say I have some data points scattered throughout the sample range, and another point that has not been measured, I want to make a prediction on. And so before I want to use that model, I want to check to see, is this a good model? Does this make sense? Can I trust this to actually launch it? All right, so as I go through the process of building my model, there's some decisions that I need to make. First and foremost, I need to think about, like, what are the possible transformations of the dependent and predictor variables I need to do? What is the form of the trend function that I want, the structure of the model? I need to think about cutoff, lag width, and possibly directional dependence for the sample variogram. So this part is very specific to spatial statistics. I need to think about my variogram model type, what variogram model coefficient values or fitted method I want to use, and size and criterion to define a local neighborhood. So this is dealing with the fact that if I'm interested in things going on in Florida and I have data for North Dakota, I don't want to have those North Dakota data in there. And if I have it in the data set, I can set criterion in there to make sure, hey, don't go too far out from the point of interest. Another aspect of it, maybe I don't, if I have a lot of data points around a particular point, maybe I only want to limit it to the closest ones on there. So size determines like how many is the maximum amount, and we can also say like how far away is worth it to even include in our model. And this can greatly improve computation time for us. And usually if we trim things down, we probably won't suffer a model derogation from trimming down number of points, as long as I have a decent sample size. All right, so let's talk about cross-validation residuals. Okay, so the author calls this just a little bit different than standard terminology of what I learned. All right, so first we're going to talk about train validation test split when we're building our model. All right, so what I'm going to do, I have my data. In my data, I have location, I have the target variable, and I have potentially covariate predictor variables that I want to use to predict that target variable. Okay, so I have rows and rows of data and columns corresponding to each of the variables I just talked about. All right, well, the idea here is I want to have a more realistic idea of how the model will perform down the road. Also, I want to select the best possible model. Okay, well, one thing that will happen is if I build a model and then I use the same data to check how well the model will perform for future, I'm going to get very optimistic results. Whatever data I put into my model building algorithm, that model building algorithm is going to be like a heat-seeking missile and fit to that data set as well as it possibly can. All right, now here's the problem with that. My data will never perfectly represent the population I'm interested in. No matter what I do, that's always going to be the case. Even if you assume that the population doesn't change for your data, there will always be a difference. Just like and we model this as just random variation, and that's just part of the field. All right, so what I want to do is I want to get more of an honest estimate of how it will actually perform, because we know that if I build a model with data, any statistics on that model using that building up data will be optimistic. Okay, so what we're going to do, I'm going to split my data into 3 groups. All right, I'm going to take the training set, I'm going to have validation set, and then a test set. The training set, this is the data that I build the model with. Okay, and so that is its purpose. Next, I'm going to have the validation set. Now, the validation set is the set that I'm going to use to check to see which of multiple models is the best one. When we go through this process, I might build possibly 100 different models. That is, depending on the size of the project, I might build quite a few models going on. Usually it'll be a smaller number, something less than 10 more than likely, but potentially if it's a huge project, lots of data, I could build a lot. All right, so for my validation sets, what I'm going to do after I've built all my models, the validation set has not been touched, has not been looked at, has not been used at all. I'm going to take it, I'm going to drop them into the models that I've already built. Then I'm going to use those. So I have the known value for the target variable on the validation set, and I have the output from the models. I'll compare and I'll check model quality. Whichever one is the best or nearly the best, using a mixture of numeric values and subject matter knowledge, whichever one is the overall best, I'm going to use, and that's going to be the model I'm actually going to use when I launch things in production. Now, there's a problem here. If I build a lot of models, so let's say that I went through and I built 100 models. Well, realistically, there's going to be flukes in the data where in my validation set, just by a fluke, just by happenstance, one model structure looks better than it really should compared to all the others. And so whichever one is my best, I can't trust it to be that optimistic of a result, because I went through time after time after time with 100 different models, and it's going to end up that whichever one was the final best, it was just kind of dumb luck that particular model was the best one. So once again, the validation statistics will be optimistic compared to what I expect to see down the road. Training set will be very optimistic. Validation set statistics will be optimistic. So I want an honest to God, as honest as possible, estimate of how the model will actually perform when I launch into production. This is where the test set comes in. I'm going to take the test set, drop it into that last final model, and I'm going to check to see it's the statistics I get for how well it's going to perform. Since the test set has not been touched, has not been used so far, this is what we call my honest estimate of what's going to happen. Okay, so spoiler, and I shouldn't say spoiler because I'm going to spoil something about this, is that in my experience, the test set is still optimistic compared to what will actually happen. The reason for that is because the population of your data is always changing in real life. So expect your test set statistics to be a little bit optimistic, and but in the ballpark of what you can expect to see when you actually launch your model. So our 3 data sets that we partition our data. is training set, validation set, test set, and we use them in that order. Training set, we build the model. Validation, we use to select our final model. Then test set gives us an honest estimate of what's going on. Me personally, in my work, usually if I don't build a lot of models, I'll just use the validation set. I'll stop at training and the validation. I'll skip the test set to have more data in training and validation. People disagree with me. The reason why I do this is because if I'm launching the model anyway, I would rather commit that extra data to training and validation. My opinion, it works for me at work, but do whatever your clients and supervisors want you to do. All right, so let's go ahead and run through an example of how to do this. All right, so first thing I'm going to do, I need to have a model to work with. In a real life project, I would have multiple models going on, and we'll compare some models later in the video. But here, just for now, just to show the concept, I've got one model using the VGM function from GStats. And since I'm going to be doing random partitioning, I'm going to go ahead and set the seed to make this reproducible so I could redo this down the road. Always a good thing to do. All right, so now what we're going to do, I'm going to sample my data into my training set right here. VTrain will be the index, will be the row numbers of the training set, and then the validation set is everything that's not in there. So in this example, I'm just doing train and validation because I only have one model going on. Really, it should be train and test now that I think about it, but whatever. All right, so something about the SP objects in the SP package, they really don't perform as well when I try to index using logical. They perform better if I use row numbers, row names for this. So you'll notice I'm doing sample INT. I could also have done this with true false statements, potentially on other data frames, but with the SP package, I can't. All right, so VTrain is a random sample of 70% of the rows in the data set. All right. And so now this will be my training set. I'm taking the subset, and the subtraction says everything that's not in VTrain, the row number wise, is going into the validation. All right, so now let's go ahead and fit our variogram. So here, I've got my variogram. I'm building it on the training data set. Here is my model structure. Log of zinc, does not have any covariates. And the model is that VGM that I defined a moment ago. Now let's get our actual Kriging model going. So there's a formula, there's location. Now on this point, my new data for prediction is my validations data. All right, so now let's go ahead and you'll notice that I pass the fit in for the model on this. And so this is ordinary Kriging because we use log of zinc depends on the intercept. And so let's take our residuals, define those. Let's get a summary of them. So now I've got an idea of the range of what's going on. And let's go ahead and compute the R squared value. So I see an R squared of 0.76. Okay, well, that's actually high enough that I could use it for work depending on what's going on. My opinion, if you see less than 0.7, don't use it. 0.76, use it, but know that it's not really strong, at least for the purpose of prediction. Remember that when we're working on this, there's a balancing between need and how accurate it is. We might want to go, I would actually want to go back and start putting in some extra covariates to improve the model, but that's all right. We're following the author's examples. All right, so let's go ahead and create a bubble plot. And so here, remember that I defined the residuals. So the observed minus the modeled is my residual. So if I have positive, that means that the observed was bigger. If I see negative, I know that the observed was smaller than the modeled value. All right, so we can see here that these are where the larger than the model values are, everywhere that's green, and here it's smaller. So this tells me that the model does a poor job picking up along the river on this part, and then the river curves around back here, and it's on the low side here. So I would want to maybe consider where we are in relation to the flow of the river when I modify the model. All right, now let's talk about Enfold cross-validation. Okay, so what we're going to do here is I'm going to partition my data into two sets. Before we had three, now it's two, but this is still going to be a little bit more complicated. I'm going to do a train validation and a test set. Now, after I do that test set, I put over to the side, train validation, I'm going to split that into in subgroups, in sub-partitions. Okay, now the game plan here is I'm going to select one of those partitions, and then I'm going to build a model with all of the others of that train validation partition. And then the one I picked is what I use for validation. So when I pick a fold, that fold is a validation set. All other folds, all other sub-partitions are part of the train set. And then we do this over and over and over. So in the situation, if I had 10 folds, I would have 10 subsets of data, and I would iteratively go through, pick one fold. The remaining nine folds, build a model, and then I do validation on the fold that was selected, and do this 10 times total. Why do we like this? Well, this gives us a distribution of the statistic of interest when we look to see model performance. Also, I find that this is a good way for checking to see, do I have any outlier problems? If you see that a model performs better on the validation set than on the train set, that's a sign that you have an outlier in your training set. Just an easy way to spot that if it comes up. And so we build the model, remember, with all the data that's not in the fold that were selected, and the fold that is selected is our validation sets. And we do this in times. Now here's some code that I built up for this. This is very different from the textbook. I just went through and did it the way that I'm more comfortable with. I'm doing threefold cross-validation. What I prefer to do professionally is I like to do repeated twofold. So I do twofold cross-validation multiple times with random splits every time. I find that's pretty fast, gives me distribution, and works out well. But so here I'm going with 3 as the number of folds, and I just go through, and here I'm just setting up data frame for each of these. All right, so this data frame tells me for each row which partition it is. And so this was a little bit funny. This was a little bit difficult. This is, since there is a difference between base R data frames and SP objects, I had to do this in a slightly different way than I normally would, but it worked out perfectly in the end. So you'll notice that I had to have numeric values inside the SP object to be able to do my indexing. Basically, my code just had like one tiny little extra step in it to execute that I would have liked to, but this works out beautifully. This is great. And so I'm going through, I'm building 3 different models on 3 different sets. Now, for every pair of models in this, they have 50% of the same data, 50% of different data. And so I've got 3 ordinary creating models. Now, what I want to do is I've got all of these different things, there. I'm going to go through and I'm going to put them all together into one data set. So I'm going to use the map tools, SPR binds, and this function didn't taking lists. So I had to do this iteratively. This isn't the best possible way, but this worked because of how SPR bind works from map tools. I established the first output from the creating model. Then for each subsequent fold after that, I just appended it onto the bottom of the data frame. And along the way, I made sure I had the rows tacked onto my output. Now this is the original row that when it came from as it came out of the box to me, and then I'm shuffling everything, I'm reordering everything to be in the original order by which it happened. That way I have the same output that I had, the same order output that I had when I first opened up the box and looked at my data. And so now let's go ahead and take a look at my mean absolute error. So the mean absolute error, so this is log of zinc minus the predicted value. So the predicted value is predicting the log of zinc. And so when I look at this, I have to consider this is the average absolute error on the log scale. Okay. And so, and this is base E log. So here is, an average mean absolute error of about 1.4. Now that's the manual way. We can do this in an automated manner, and usually you want to do the automated way unless you have a good reason not to. If there's some lacking and there's something that you want to get out that the code doesn't support, you can do it manually. But I would recommend that you go ahead and use the in-house cross-validation function to do this quickly for you. It's very nice. You specify a number of folds. You're going to want to suppress the output so you don't get a ton of stuff blasted in the face that you don't want to look at. And then it just organizes everything nice for you. It's really nice. And so when I get the output, I can go ahead and do that plot. I don't have to put my data back together. Don't have to reorder anything. Everything is done under the hood for me. And so now I can see, well, it looks like once again that the model is coming low on this part of the river and the model is high compared to this part of the river. So that tells me that I probably want to consider where the point is closest to the river. All right, so something else I can do, I can change the maximum size and the colors. So something I don't like about those plots we just looked at is that green gives the impression of like red and green. Red is bad, green is good. These are residuals. They're all bad. So here I modified it just so that we could have more of a neutral plotting effect in terms of interpretation. All right, so something that we could also do, we can take a look at the Z-scores to standardize our residuals. Now, something that's funny about this is I have to consider which standard error do I divide by. All right, so what we're going to do, we're going to divide by the standard error for the location that we are interested in. So we get an estimate of the standard error at the modeled location. So then what I'm going to do is use that to figure out what's going on. I'm not going to use for the entire model, for the entire sampled region as a whole, only the spot I'm interested in. All right, so if all of the assumptions of the creating model are met, then Z will be, our target variable will be normally distributed, and the Z-score will have approximately mean of 0 and standard deviation 1. All right, so let's take a look at what do we get out. Notice that in my I use the SP summary function. So if I use just regular summary without that SP package notation, it's going to just give me basic aspects of the object that's true to base R when base R doesn't know how to grab the actual values of interest. And so here we can look at the Z-scores of the residuals and get an idea of what's going on. Mean of 0, all right. Median, I shouldn't say 0. Nearly 0 for the mean, nearly 0 for the median. They're close together. That makes you feel like pretty close, probably pretty close to symmetric distribution. I'd have to actually look at the plot and dig in, but just as a quick glance, That is looking good to me. Looking here, all right, this is a little bit less extreme than -2, a little bit more extreme than 2, but didn't reach 3. Probably all right. Not seeing too much. Now for multivariable models, it gets a little bit more complicated. And what we're going to want to use is the GStat cross-validation function. And so remember that this is going to be the output of a GStat function itself. All right, so this is when I want to have multiple variables being modeled at the same time. Now, something that is important about the output we get from these is, are we going to say remove all or all residuals? And this is true or false. Remove all removes observations at cross-validation locations, not only for the first, but for all subsequent variables as well. All residuals for a variable are returned instead of for the first variable only. All right, so one of the default features of this function is that it wants to work with only the first variable of multiple. And so if I want to have multiple variables taken care of at the same time, I have to adjust this parameter. Or I can manually enter it, and I'll show you how to do that in a moment. All right, so if I leave it, or if I take GStat cross-validation, and I say remove all residuals both false, here we can see what our output is. And here we've got that. And you'll notice that I've only got one variable going on. All right, there's a lot of output on this, unfortunately. So I have to scroll through it. Now here I'm going to say remove all is true, all residuals is false. And so here we have the target variable. And so it only gave me the first there. Now, what's going to happen if I was to say remove all is false, all residuals is true, then you'll notice that it sets it up to give me all the variables, but I get zeros on the other 3 variables in the model. Not very useful. I would have been better off with the other outputs. Honestly, there would have been more information. Now, if I go true, true, I get residuals for all 3. Or sorry, all four. Now, another way that we can do this is that if I pass the variable of interest into the GStat object, so if I take log of the variable and I put it in the GStat multiple, just like I would with a list, it'll give me the output. So what I'm doing here with this lapply function to do it fast, quick, and easy, I'm saying, hey, give me one variable at a time, the output. And so here is for the first one. Here's for the second. Third and fourth. And something that's nice about this is that I get the predicted value, the actual observed, the residuals. It all comes out very quickly for me when I do it this way. Oh, now you'll notice the coordinates are off. That's because in the display, the printing within our markdown, I said to reduce the number of digits displayed down to 2 to round off to make things easier for us to read. All right, now there are some limitations to cross-validation. So first and foremost, cross-validation only works on a model I've already established, I've already built. So it doesn't tell me what is the right model. It evaluates what's the model I already have. So if I'm missing something, if I'm confused, if I did something wrong in my model building, it won't necessarily tell me that. Specifically, if I get the wrong model structure, it's not going to go, hey, go to this one over here. It just checks, what do I have? So it doesn't tell me what the model structure should be, nor does it include what variables should be in there, nor what parameters to include, transformations, it doesn't say. We have to use our subject matter knowledge and experience with similar data to know how to approach that phase. All right, so if I make mistakes on all of my model, let's say I think it should be of a certain type and I run with that type, but it's a bad type, and I've just got variables thrown into there, different variables, different transformations, it's a bad model structure. If I have all poor models, then my best validation model will still be a poor model. So we won't really know if we're in the situation unless we use subject matter knowledge, or if we just keep trying different things to, to compensate for this. And so let's go ahead and compare two models. So here I'm going to build up two models here using VGM once again. And I'm setting the seed, setting up cross-validation. Now this is going to run through everything easy peasy for me. And now I'm going to get the mean absolute error of each of these. All right, so we can see that they're pretty close. If I had more decimal places observed, we would see like what the actual difference is. One performed better than the other, but we can see that really they're pretty close. Now what we can do, let's check to see how their variances at the score locations compare. All right, so we're going to go ahead and run through the Kriging model process for each of these, ordinary Kriging both times. Now let's get the summary. All right, well here I'm going to take the variance minus the variance. And so if I get a negative value, I know that the model 3 is giving me a larger variance than model 2, okay? And here, we're rescaling just so that we have an idea of how this compares based off of model 3 as being our baseline. And so I can see a negative minimum, first quartile, median, mean, and third quartile. So overall, at most locations, model 2 is giving us a smaller variance. It's not 100% of the time. We can see that this is a pretty big value. This is probably going to be a little bit of skewing, maybe just a few. But so if I'm getting practically the same accuracy, but one model has lower variance, I'm going to choose the one with lower variance. All right, well, that's all I've got for you. Take care and goodbye.